Hi everybody, Namaste and welcome to Murali's World of Physics once again.
This video forms part 4 of a series of videos on unique numbers in mathematics and physics. In the earlier 3 videos of this series, we had dealt with some unique integers and irrational numbers of much importance in mathematics and which had some relevance in physics also. Now we are going to discuss in this video some such integers and irrational numbers especially useful in the realm of physics.
When we come to physics, there are a large number of unique numbers which are commonly referred to as the fundamental constants in physics. These are believed to be both universal in nature and also time invariant. Most of them refer to constants of proportionality which appear in several equations which pertain to corresponding physical phenomena, and these are determined experimentally by conducting actual physical observations of those phenomena. So in this aspect they are completely different from the constants in mathematics, which are not at all connected with any experimental determination. Now, some of these fundamental constants in physics are pure numerical constants which do not possess any units associated with them. Others have appropriate units that go along with these numerical values. The absolute numerical magnitude of these fundamental constants which have associated with them certain units will of course depend on the choice of that particular unit in which that particular magnitude is expressed. Of course, the physical quantity itself to which the numerical constant refers does not depend on the actual units in which that is expressed.
Historically, the first place that integers appeared in physics was the periodic table of elements. Here, the integers label the elements, which we now know count the number of protons inside the nucleus. Also, this represents the number of neutrons and number of extranuclear electrons in the atom. They are also the very soul of quantum mechanics in the form of quantum numbers which designate the energy levels of atoms, nuclei, etc. Also, integers naturally evolve in any discussion of entities which occur in chunks, that means in quanta. Quantization means that an integer represents a whole physical system. In other words, a physical state or system is recognized by a number. Interference and diffraction in optics are phenomena that are related to waves, and their explanation also involves integer quantities. These are also used to represent quantized energy levels, quantized angular momenta, etc. in quantum mechanics. Number theory has also played a crucial role in quantum information, starting from the Shor's algorithm that reduces the exponential cost of factorizing integers in a classical computer to a polynomial cost using a quantum computer. The recent construction of small quantum computers suggests that quantum algorithms based on number theory will play a fundamental role in the near future with a huge impact in basic sciences and technology. One very important set of integers crucial to nuclear physics comprise of what are known as the magic numbers. Now, what are these magic numbers? These magic numbers are 2, 8, 20, 28, 50, 82 and 126. Of course, these are not fundamental constants of physics but still very important. Such numbers indicate exceptional stability for nuclei having magic number of protons or neutrons. A few of the so-called magic nuclei are helium 4, oxygen 16, calcium 40, nickel 64, tin 120, lead 208, etc. The most fundamental of all physical constants is probably the Planck's constant. It is also probably the smallest of all such constants. The magnitude of Planck's constant is 6.62607,015 into 10 raised to minus 34 expressed in units of joule seconds. This represents the smallest chunk of energy of electromagnetic radiation, or in other words, quanta of electromagnetic radiation. This was introduced first by the German physicist Max Planck in the year 1900, and he used it to explain the spectral distribution of the electromagnetic radiation emitted by a black body at a given temperature T in thermodynamic equilibrium. This is a graphical representation of the intensity distribution of the black body radiation at three specific temperatures T1, T2 and T3, with T1 less than T2 less than T3. Planck was able to explain the shape of this distribution only when he imposed the condition that the electromagnetic radiations are quantized with respect to their energy, which is proportional to the frequency nu. The proportionality constant is what is known as the Planck's constant. Thus, the energy of the quantum is given as E is equal to h nu, where h nu is the frequency of the radiation. Expressed in the form of an equation, Planck's radiation law is U nu as a function of the frequency and temperature is equal to 8 pi h nu cubed by c cubed into 1 by e raised to h nu by kBt minus 1, and expressed in terms of lambda and t, the wavelength and temperature, this is given by 8 pi hc by lambda raised to 5 into 1 by e raised to hc by lambda kBt minus 1. Of course, here nu is the frequency and lambda the corresponding wavelength, and kb is the Boltzmann's constant, and c is the speed of light. Both kb and c are fundamental constants which will be explained later. The famous photoelectric equation also involves the Planck's constant h. This equation was derived by Albert Einstein in his explanation of the special properties of the photoelectric effect, which could not be explained by classical physics. The process involves the absorption of energy from an incident radiation of frequency nu by an electron inside the atom of an element and the subsequent ejection of the electron. So, diagrammatically this process can be represented like this. We have a material and light is incident on the metal surface, and the interaction results in a transfer of energy from the incident light to the electrons in the medium, and the subsequent ejection of these electrons from the material. So these ejected electrons are known as the photoelectrons. Einstein's equation reads E is equal to h nu minus E phi, where E is the kinetic energy of the ejected electron and E phi is the binding energy of that particular electron to the atom. This is also known as the work function. The extreme smallness of the magnitude of the Planck's constant makes it difficult for us to appreciate the quantum nature of light in the real macroscopic world. It will be interesting to contemplate on what will happen if the magnitude of h were much larger. Obviously, physics will not be the same as it is now. The magnitude of h is crucial in understanding the scale at which quantum effects become significant. Definitely, we will start feeling the quantum effects in our day-to-day life if the magnitude of h were larger. If we integrate the expression for the energy distribution of blackbody radiation, we arrive at the total energy radiated. Integral from 0 to infinity I lambda d lambda is equal to integral from 0 to infinity 2 pi h c d lambda by lambda raised to 5 into e raised to h c by lambda kt minus 1, and therefore one can finally arrive at the result that this will be equal to sigma t raised to 4, where sigma is a constant defined by this particular expression, and it is known as the Stefan-Boltzmann constant. The magnitude is 5.6073 into 10 raised to minus 8 watts per meter squared per Kelvin raised to 4. This is the so-called Stefan-Boltzmann law. Usually h appears in many equations as a combination with the factor of 2 pi, and it is called h bar equal to h by 2 pi, that is equal to 1.054571817 into 10 raised to minus 34 joule seconds. So it is pronounced as h bar or h cross. Since the units are those of energy times time, Planck defined this as an elementary quantum of action. Action is defined as the integral s is equal to integral from time t1 to t2 of the Lagrangian of the system into dt. The integral is over the trajectory of the particle in its motion from time t1 to t2. This can also be written as s is equal to integral from q1 to q2 p dq, where p is the momentum and q is the coordinate. Classically, this is a continuous variable. However, in the quantum world, Planck introduced its quantum feature. That means S is equal to integral from t1 to t2 L dt is equal to an integer times the Planck's constant. Actually, the integral S measures the change in action when the object or system moves from one place to another over a certain time period. Quantization means that such motion can take place only in quantized steps, which results in quantum change in the action. Of course, the extreme smallness of the absolute magnitude of H makes it impossible for us to detect the effects of the action quantization in our macro world. Its effects start becoming prominent only when we delve into the world of micro and submicroscopic particles and the elementary particles like atoms, nuclei, etc. Dimensionally, the Planck constant is equivalent to angular momentum also. In fact, h cross is also the quantum of angular momentum. For any quantum system, the total angular momentum inclusive of the spin is given by J is equal to L plus half h cross, where L is an integer running from 0, 1, 2, 3, etc. Planck's constant also appears in many other formula related to the quantum regime. For example, the Heisenberg uncertainty relations gives the uncertainty product of correlated errors in the coordinate and the associated momentum will be greater than or equal to h cross by 2. That means it is impossible to know both the exact position and the exact momentum of an object simultaneously. The variables energy and time are also related through a similar uncertainty relation as given here. Delta E into delta T is greater than or equal to h cross by 2. So this h cross by 2 happens to be the minimum uncertainty product. It is also impossible to measure both time and energy simultaneously to an infinite precision. This can also be interpreted as follows. An uncertainty in energy conservation is allowed to within a period as defined by the above relation. Now coming to experimental determination of Planck's constant. The simplest method is to make use of the photoelectric effect. We use light emitting diodes of different wavelengths or frequencies and measure the energy of the ejected photoelectrons by applying a suppressing potential to stop them. The wavelength or the frequency is measured using a diffraction grating. The result of a particular experiment in photoelectric effect is shown here. So here the slope of the straight line fit used to obtain the value of Planck's constant. Now there is a famous principle known as the wave particle duality and associated matter waves. Every particle or quantum entity may be described as either a particle or a wave. This is the so-called dual nature of matter and waves. A particle of momentum p has a matter wave associated with it with a wavelength lambda is equal to h by p. This lambda is known as the de Broglie wavelength. Now this is most vividly revealed in the case of light. Phenomena like interference and diffraction reveal the wave nature of light, obviously. So this is the double slit experiment and the observed interference pattern, and this is the diffraction from an aperture and the observed diffraction pattern. So these phenomena refer to the wave nature of light. On the other hand, phenomena like the photoelectric effect and Compton scattering reveal the particle nature of light. So we have already seen the photoelectric effect. Light incident on a metal surface leads to ejection of electrons provided the light energy is more than a given threshold, which is particular to that particular material. So this reveals the quantum nature of light. Also in Compton scattering, which is the scattering of the incident light by an electron inside an atom in a material and the subsequent ejection of the electron in a particular direction. The electron gets enough energy from the incident photon to get ejected from the atom. So here also the quantum nature of the incident light is evident. So that means light consists of quanta of radiation called photons. The dual nature is exemplified through the following relations for a photon of energy E, momentum p and the corresponding electromagnetic wave with wavelength lambda and frequency nu. E is equal to hc by lambda and equivalently the momentum is equal to E by c that is equal to h by lambda. Similarly, in the case of electrons, which are particles, it is a well established experimental fact that they exhibit diffraction phenomena just like light waves. So this is a particular experiment in which the electron diffraction is observed, and this is the observed diffraction pattern, which is similar to that of the diffraction in the case of light. Einstein's famous equation for photoelectric effect, as we have already seen, E is equal to h nu minus E phi, where E phi is the work function, and this gives the binding energy of the electron. The smallest amount of energy that can be emitted or absorbed in the form of electromagnetic radiation is what is known as a quantum. And we have already seen that the quantum energy is given by E is equal to h nu. Now, another important fundamental constant of physics is the velocity of light c. It is the velocity with which light travels in vacuum, and it is a universal constant. The speed of light has been determined to be exactly c is equal to 299,792,458 meters per second. All forms of electromagnetic radiation, including visible light, travel at the speed of light. This particular constant can be used in time of flight measurements to measure large distances to extremely high precision. It was Paul Drude who in 1894 first used the symbol c for the velocity of light in vacuum. Massless particles and field perturbations such as gravitational waves also travel at the speed of light in vacuum. Such particles and waves travel at speed c regardless of the motion of the source or the inertial reference frame of the observed. This is the so-called special theory of relativity which was suggested by Albert Einstein. Particles with non-zero rest mass can be accelerated to approach c but can never reach it, regardless of the frame of reference in which their speed is measured. In the special and general theories of relativity, c correlates space and time and also appears in the famous equation of mass-energy equivalence, namely E is equal to mc square. The speed at which light propagates through transparent materials such as glass or air is of course less than c. Similarly, the speed of electromagnetic waves in wire cables is lower than c. In fact, the ratio between c and the speed v at which the light travels in a material is called the refractive index of the material, n is equal to c by v, and is the characteristic of that particular medium. Now let us see how the value of c can be measured experimentally. Of course, the simplest and accurate approach is the traditional one by measuring the distance L travelled in a known time interval t. Then of course the speed of light is given by L by t. So L is the total distance travelled by the light from the source to the detector after, of course, if required, a reflection from a mirror, so that we can have a longer value for the total length. And these photons are sent from the source s at time t1 and are received at time t2, so that the time interval is t is equal to t2 minus t1, and therefore the velocity will be given by L by t. Here light from a laser source is reflected by a mirror kept at a large distance, and the reflected light is detected by a photodiode. The time delay between the laser pulse and the diode pulse is accurately determined electronically via fast electronic circuits. Another way to measure the speed of light is to independently measure the frequency nu and wavelength lambda of an electromagnetic wave in vacuum. The value of c can then be found by using the relation c is equal to nu lambda. Of course, here a particular case is shown. So this starting position of the wave, and this is the position after 1 second. So you can see that 3 wavelengths have been advanced by the wave. So obviously the total length covered in 1 second is 3 lambda. So therefore the velocity is equal to 3 lambda. For this purpose, one option is to measure the resonance frequency of a cavity resonator. If the dimensions of the resonance cavity are also known, this can be used to determine the wavelength of the wave. The fundamental constant c occurs in many formulae in physics. Of course, one we have already seen, Einstein's mass-energy relation, E is equal to mc square. Also, the relativistic length contraction. The corresponding factor is given by gamma, which is equal to 1 by square root of 1 minus v square by c square. the relativistic mass increase is given by m is equal to m0 by square root of 1 minus v square by c square. The time dilation factor, which is so beautifully illustrated in the case of the lifetime of mu mesons, which reach the Earth along with the cosmic rays. In modern quantum physics, the electromagnetic field is described by the theory of quantum electrodynamics. In this theory, light is described by the fundamental excitations or quanta of the electromagnetic field, which are called photons. In quantum electrodynamics, photons are massless particles, and thus, according to the special theory of relativity, they travel at the speed of light in vacuum. Naturally, the speed of light appears in equations related to electromagnetism, such as Maxwell's equations. Also, in the Compton effect, the change in wavelength of the photon scattered through an angle phi, this is known as the Compton shift, is given by delta lambda is equal to lambda prime minus lambda is equal to h by mc into 1 minus cos phi. According to Maxwell's equations, the speed of light c is related to the electromagnetic properties of vacuum. C is equal to 1 by square root of mu 0 epsilon 0, where epsilon 0 is the permittivity of free space and mu 0 is the magnetic permeability of the vacuum. Now, these electromagnetic properties are also fundamental constants, and this will be explained slightly later. The next important fundamental constant is the Boltzmann's constant, designated by Kb. This is the physical constant relating to the average kinetic energy of gas molecules to the temperature of the gas, and the magnitude is Kb is equal to 1.3806452 into 10 raised to minus 23 joules per Kelvin. The Boltzmann constant appears in practically all areas of thermal physics and a very statistical formulation of both classical and quantum physics. It also appears in Planck's law of blackbody radiation as well as Boltzmann's entropy formula. The constant can be defined as the proportionality constant between the thermodynamic temperature of a gas and the average relative kinetic energy of the gas molecules. For a classical system at equilibrium at temperature T, the average energy per degree of freedom is given by Kb into T divided by 2. The Boltzmann's constant has the same unit as entropy, which is energy divided by temperature. In the kinetic theory of gases, the Boltzmann's constant appears in the formula for the Maxwell velocity distribution of gas molecules at a given temperature T. So the expression for this distribution is given as F is equal to 4 pi v square m by 2 pi kb T the whole raised to 3 half e raised to minus mv square by 2 kb into T. V is the velocity of the molecules, kb is the Boltzmann's constant, T is the absolute temperature, and m is the mass of the gas molecules. So here a plot of this distribution as a function of velocity at 3 different temperatures is shown. The so-called molar gas constant R is defined as the product of Avogadro's number and the Boltzmann's constant. R is equal to Na into Kb. This R appears in the famous ideal gas law Pv is equal to RT, where P is the pressure and V is the volume of the gas at a given temperature T. The most exact measurements of the Boltzmann's constant were made in 2017 using what is known as the acoustic gas thermometry. Here the speed of sound of a monatomic gas of molar mass m is measured in a triaxial ellipsoid container using microwave and acoustic resonances is determined. So Kb is given by this particular formula, where gamma is the ratio of these heat capacities. For the simplest example of a gas consisting of Na non-interacting atoms, and this particular quantity is known as a 1 mole. Each atom has 3 translational degrees of freedom. Hence the total thermal energy of the gas is 3 Na into Kb into T by T. That means 3 R T by 2. What are the other applications of Boltzmann's constant? It is employed for the expression of the equipartition of the energy of an atom in classical statistical mechanics. It also expresses the Boltzmann factor e raised to minus beta E, where beta is equal to 1 by kBt. This is the relative probability of a molecule possessing an energy E above the reference energy E is equal to 0. The Boltzmann's constant plays an important role in the definition of entropy from statistical point of view. The entropy is given by Kb logarithm of W, where W is the number of microstates corresponding to the given macrostate. Next, it is employed for the expression of thermal voltage in the field of semiconductor physics. This is the voltage created by the junction of dissimilar metals when a temperature difference exists between these junctions. That means Vt is equal to kBT by E. For example, at 300 Kelvin, thermal voltage is approximately equal to 25.85 millivolts. In the Shockley diode equation, thermal voltage is equal to Vt is equal to kBT divided by E, where T is the ambient temperature and E is the charge of an electron. It's also the relationship between electrostatic potential and the electric current across a PN junction. The general form of the Eyring-Polanyi equation is given by K is equal to kappa kb T by H e raised to minus delta G by RT. This describes the changes in the rate of a chemical reaction against temperature. Now K is the rate constant, delta G is the Gibbs activation energy, kappa is the transmission coefficient, Kb is the Boltzmann's constant, T is the temperature, and H is the Planck constant. Again, the Arrhenius equation giving the dependence of the rate constant of a chemical reaction on the absolute temperature as K is equal to A e raised to minus Ea by RT. Ea is the so-called activation energy. Also involves the Boltzmann's constant. The system in equilibrium at a temperature T generally occupies a state I with probability Pi and energy Ei weighted by the corresponding Boltzmann factor. Also the partition function Z. The next important constants in physics are the pair of fundamental constants from electromagnetism. These are the two electromagnetic constants epsilon 0 and mu 0. They appear in the basic equations for the electric and magnetic fields from electric charges and currents. Epsilon 0 is the permittivity of free space. It's a physical constant that reflects the ability of electric fields to pass through a classical vacuum. The magnitude of this constant is equal to 8.854 into 10 raised to minus 12 farads per meter. It is also a measure of how intense an electric field is permitted to form in response to electric charges. It formally appears in the expression for the force between two separated electric charges in the vacuum of classical electromagnetism given by Coulomb's law. So we have two charges kept in vacuum, and what is the electrostatic force between these two? So that is given by Coulomb's law. F is equal to 1 by 4 pi epsilon 0 q1 q2 by r square, where r is the distance between the two charges. So this involves the electric permittivity of free space. The so-called Biot-Savert law describes the magnetic field created by an electric current. An electric current I is passed through a long straight wire, and the resulting magnetic field is measured. So that magnetic field is described by this particular equation. B is equal to mu 0 I by 2 pi r, and mu 0 is the magnetic permeability of the vacuum and I is the current intensity. So mu 0 gives a measure of the effectiveness of an electric current in producing a magnetic field in vacuum. Mu 0 is equal to 4 pi into 10 raised to minus 7 henries per meter. The relation between the magnetic induction B and the magnetic field intensity E is given by B is equal to mu 0 into H. The electromagnetic constants appear in many formulae in electromagnetism. For example, the capacitance of a parallel plate capacitor of spacing d is given by C is equal to epsilon 0 A by d. We have already seen that the velocity of light c is related to the electromagnetic constants epsilon 0 and mu 0 through this particular relation. In fact, this was derived by Maxwell through his famous Maxwell's equations, but it is still treated as a universal constant. Also, these constants appear in the expression for the characteristic impedance of vacuum. Z0 is equal to E by H, that is also equal to mu 0 C, is equal to square root of mu 0 by epsilon 0, that is also equal to 1 by epsilon 0 C. The magnitude of this characteristic impedance is given by 376.730 ohms. This characteristic impedance is an attribute of any medium that can support the transmission of an electromagnetic wave. Now Z0 is a physical constant relating the magnitudes of E and H of the electric and magnetic fields of electromagnetic radiation traveling through free space. That is, Z0 is equal to magnitude of the electric field to the magnitude of the corresponding magnetic field. Z0 is equal to E by H. This constant is independent of length or distance over which the signals propagate and is considered equivalent to that of dry air, which has almost no effect on the conductance. Now, let's briefly see how the electromagnetic constants can be experimentally measured. experimental determination of the velocity of light and the characteristic impedance of vacuum can give the values of these constants. The formulae for these quantities we have already seen. So therefore one can rewrite those equations as follows. Mu0 is equal to 1 by c z0 and epsilon 0 is equal to z0 by c. So therefore if we experimentally determine z0 and c, then one can use these equations to calculate the values of mu0 and epsilon 0. Now the experimental determination of c we have already discussed earlier. For the measurement of the characteristic impedance of vacuum, we rely on the measurement of the electric and magnetic fields of a plane electromagnetic wave traveling through air. In any medium other than vacuum, the electric displacement and the magnetic field are related through this particular relation. D is equal to epsilon 0 E plus P and H is equal to B by mu 0 minus M, where P is the induced polarization and M is the induced magnetization in the medium. The next important fundamental constant is the Avogadro's number Na. What is Na? It actually gives the number of molecules of any gas present in a volume of 22.41 liters at normal temperature and pressure. It is the same for the lightest gas hydrogen as for a heavy gas such as carbon dioxide or bromine. The magnitude of this constant is 6.0221367 into 10 raised to 23. So this number is attributed to Avogadro. Equal volumes of gases at the same temperature and pressure contain the same number of molecules regardless of their chemical nature and physical properties. So this 22.4 liters is known as the molar volume. So the molar volumes of all gases should be the same. Now how is Na determined experimentally? One of the accurate measurements is the determination of the contents and dimensions of the unit cell of a crystal from X-ray diffraction technique, and this has been established since early 20th century. Another important fundamental constant is the universal gravitational constant G. The magnitude is 6.673 into 10 raised to minus 11 Newton meter square per kilogram squared. So this appears in the expression for the gravitational force between, for example, the earth and the sun. So we have the sun and the earth revolving around the sun in its specified orbit. So the force between these two heavenly objects. So that is given through the universal gravitational constant as a proportionality constant in the expression. I hope all of you know the famous anecdote about Sir Isaac Newton and the falling apple. Apparently Newton was intrigued by the sight of the falling apple. He contemplated about the force which made this happen. He performed some experiments and observations on falling bodies as well as on the sun, moon and earth. Finally he arrived at the famous universal law of gravitation, which reads, every object in the universe attracts every other body with a force directly proportional to their masses and inversely proportional to the distance between them. So this is expressed through this particular relation. F1 is equal to F2 is equal to G M1 M2 by R square, where M1 and M2 are the masses of the two heavenly objects or any two bodies and R is the distance between them. So this embodies Newton's law of universal gravitation. Of course the magnitude we have already seen. Now G can be taken as a measure of the strength of the gravitational force. This is to be compared with the corresponding strength constants of the other three fundamental forces of nature, which are the nuclear force, the electromagnetic force and the weak force. We immediately see that the gravitational force is the weakest of all fundamental forces. The constant G appears in many equations involving gravity. For example, the escape velocity of an object from the earth is given by V is equal to square root of 2g m by r. M is the mass of the earth and here is r is the radius. Similarly, the Kepler's third law reads a cubed by t square is equal to g into m plus m by 4 pi square, where a is the mean distance of a planet of mass m from the sun of mass capital M and t is the time period of revolution of the planet around the sun. The acceleration due to gravity is given by the following expression, g is equal to gm by r square. On the earth, g has a value of 9.8 meters per second. In Einstein's general relativity theory, the Einstein tensor g, which describes Some aspects of the way space-time is curved is given by g is equal to 8 pi g by c raised to 4 into t. Here g on the right hand side is the Newtonian gravitational constant, and t measures the matter content, which is known as the stress energy tensor. G was first measured in 1797 by the English scientist Henry Cavendish. The apparatus featured a torsion balance. A wooden rod was suspended freely from a thin wire, and a small lead sphere hung from each end of the rod. A much larger sphere was placed at each end of the torsion balance. The experimental setup is given here. This is the bigger lead balls. These are the smaller lead balls, and there is a torsion balance, and the rotation is measured by a reflected light beam. The gravitational attraction between each larger weight and smaller one draws the ends of the rod aside along a graduated scale. The attraction between these pairs of weights was counteracted by the restoring force from a twist in the wire. The deflection observed is a measure of the force between the two sets of balls, and therefore G can be measured therefrom. Although scientists have been trying to measure its value for centuries, G is still only known to about 3 significant figures as compared to most of the other fundamental constants, which are known to 9 significant figures. The next fundamental constant is the electronic charge E, which is a fundamental property of matter due to which it produces and experiences electric and magnetic effects. The fundamental charge exists as a quantum. This cannot be subdivided. Any free electric charge in the universe will be in integer multiples of this particular unit. The most accurate value of the electronic charge is given by 1.602176662 into 10 raised to minus 19 coulombs. It has been recognized that there are two kinds of electric charge, positive and negative. Their property is such that like charges repel and unlike charges attract. Conventionally, the charge on the electron has been taken as negative. Numerically, E is also equal to the positive charge on the elementary particles such as protons. Now, there is a famous conservation law of charges. This is a fundamental conservation law similar to those for mass energy, momentum, etc. The credit of the discovery of the fact that amber rubbed with wool or silk cloth attracts light objects goes to Thales of Miletus, Greece around 60 BC. In fact, the Greek name for amber is electron, which is the origin of all such words: electricity, electric force, electric charge, and electron. So here two examples are shown where electric charge is produced by rubbing, let's say, amber on wool or glass on silk. The electronic charge was identified and measured by Millikan in his famous oil drop experiment in 1909. This is a particular schematic diagram of the setup used by Millikan. So we have oil drops sent into a vacuum chamber. So here, while spraying, these oil drops get electrified and they move down accelerated by gravity. Over a certain distance, they are subjected to an electric field in the opposite direction, which opposes their motion under gravity. So by balancing these two forces, one can actually measure the electronic charge. From the measurements of the applied field necessary to keep the droplets stationary, Millikan could determine the charge on the droplets. He observed that these charges occurred in multiples of a unit charge E, and he determined the magnitude of this charge E. Earlier in 1897, Thomson had measured the ratio of the charge to mass of an electron in an experiment which comprised of subjecting a beam of electrons simultaneously to electric and magnetic fields so that the net deflection of the beam is null. From the measured electric and magnetic fields, the ratio E by m0 was evaluated, and this came out to be E by m0 is equal to 1.758820 into 10 raised to 11 coulombs per kilogram. Combining the two measurements of Millikan's and Thomson's, the electronic rest mass m0 can be evaluated as m0 is equal to E divided by E by m0, and the magnitude came out to be 9.109383715 into 10 raised to minus 31 kilograms. Another method to determine M0 is to accurately measure the energy of annihilation photons in a positron annihilation experiment. Positron interacts with an electron in the material, they annihilate and gives rise to 2 gamma photons. The energy of each gamma photon will be equal to the rest mass energy of the positron or the electron. Now, apart from the fundamental constants, there are several constants in physics which are derived from the fundamental constants discussed so far. I will just give 2 examples. The first one is the fine structure constant alpha, which is defined as 1 by 4 pi epsilon 0 e square by ch cross, and the magnitude is 0.00729735256993, which can be approximated to 1 by 137. So in approximate calculations one can take 1 by 137. Alpha indicates the strength of the interaction between charged particles. It plays a crucial role in the realms of quantum mechanics and electromagnetism. There are other names for the constant like the coupling constant or the Sommerfeld constant, in honor of Arnold Sommerfeld, who introduced this particular in his study of the atomic spectra. The term fine structure constant originates from its role in explaining the fine structure of atomic spectra, especially the spectral lines of hydrogen. The energy levels of hydrogen are given in terms of the fine structure constant. En is equal to minus alpha square me c square by 2n square, where n is the quantum number representing the particular quantized energy level of the hydrogen atom. Scientists measure the value of alpha using various methods, including observing the spectral lines of atoms, the quantum Hall effect, or the anomalous magnetic dipole moment of the electron. The other derived fundamental constant is the Rydberg constant R infinity. It describes the wavelengths of spectral lines of atoms. 1 by lambda is equal to R infinity into 1 by n1 square minus 1 by n2 square, where n1 and n2 are the quantum numbers of the 2 energy levels between which the transition takes place, resulting in the particular spectral line. The expression for R infinity in terms of the other constants is me e raised to 4 by 8 pi epsilon 0 squared h cubed c. The value can be easily and accurately measured experimentally by a study of the spectral lines in the Balmer series of hydrogen atom using a diffraction grating. I will end this video at this point. If you like this video, kindly click on the like button and share with your friends and relatives, and also with your different groups. If you have not already subscribed to my channel Murali's World of Physics, kindly do it now. And please don't forget to click on the bell icon so that you will receive notifications in future about my upcoming videos. I'll be back soon with yet another video on basic principles in physics. Till then, goodbye.